Okay, so let's look at number 4 from worksheet 12. So there is a solenoid that has the length of 25 centimeters, and it has the number of turns is equal to 600. So N1 is 600, and its diameter is 2.5 centimeters, but in meters it would be 0.025 meters. And there is a circular coil that tightly wounds the solenoid. So let me use a different color to show the circular coil. So we have this circular coil that has the number of turns of 14, and 2 is 14. So the current through the solenoid is changed from 0 amperes to 5 amperes in 0.6 seconds. So that means we are changing current by 5 amperes in this solenoid in delta t is equal to 0.60 seconds. Okay, so we know that there is current going through this solenoid, and when there is current in the solenoid, it produces magnetic field, and the magnetic field inside the solenoid is more or less straight like this. That's the magnetic field, and it's because of the current in the solenoid. And the magnetic field produced by the solenoid is given by mu naught, number of turns of the solenoid, which is N1, and the mu naught Ni, current through the solenoid, over the over the length of the solenoid, which is L. Okay, that's the magnetic field, and this magnetic field is also shared by this circular coil. Okay, so this is shared by the circular coil. And we also know that this I is changing, the current is changing, which is that. And because of the change in I, there is also change in B. Okay, so that means if this is the circular coil and there is magnetic field going through the circular coil, okay, and we know that when there is magnetic field going through the circular coil, we have the flux, because flux is BA cosine theta. So that's the flux through this coil, and because this B is changing, which is this magnetic field, that means we have change in the flux with time. So we have delta phi over delta t, and Faraday's law tells us that whenever there is change in flux, that induces the EMF or current. Okay, and that's what we want to find. So Faraday's law tells us that EMF is equal to minus, I will neglect the minus sign for now, because we are only trying to find here the magnitude. So N delta phi over delta t, and delta phi is BA cosine theta. So magnetic field, area of the loop, cosine theta over delta t, and the circumference of this loop and the circumference of the solenoid would be same, because this circular loop is tightly wound around this solenoid. That means circumference of both the coil and the solenoid would be 0.025 meters. No, that's the diameter, sorry. So circumference is, we know it's pi d, and so pi times diameter is 0.025 meters. Okay, so that's the circumference. And if I want to find the radius, to find the area I need radius. So circumference is 2 pi r, pi 0.025 meters. I could have just used half of that, but I want to show here they have the same circumference. That's why I'm using this math. So you can cancel that and that. So r would be half of the diameter because they have the same diameter. So that would be 0.0125 meter. Okay, so we'll be using that for the area, but for now let's just use the symbol. We'll plug in the numbers later. Area, we are keeping area constant. Pull it out of the delta because again it's not changing. Cosine theta, the orientation is also not changing, so pull it out. So we are changing only b, which is again because of changing I. So this b changes because of the I. Okay, and this n is the number of loops in the coil, because we are talking about the current produced in the coil. So this is coil, which is N2, and that's the area of the loop. So let's call that A2. So that's N2, A2 cosine. Magnetic field is pointing this way, and area vector is also pointing in the same direction because area vector is perpendicular to the surface of this coil. So they are parallel. That means cosine theta would be cosine 0 degrees, and the value of cosine 0 degrees is 1. So this could also be just be written as 1. And delta B, this magnetic field is again due to this current produced in the solenoid. So delta mu naught n. Now this is the thing in the solenoid. That's why I'm using 1 here, not 2, because that's the number of turns in the solenoid, and that's the current. Okay, and that over L over delta T. Okay, so this is that, and delta B is delta that thing is B, and we have delta T. Okay, so mu naught is constant, we can pull that out, and N1 is also constant, that's the number of turns in solenoid, and L is also constant. So pull all the constant terms out of the delta. So cosine 0 degrees is just 1. I will not write that. So we have mu naught constant, N1, and that over I, that over L, sorry. So that over this L. Okay, and then we have delta I, because it's changing, so I will keep the I inside the delta, and then we have delta T. So now we will just plug in the numbers in this. So N2 is 14. Now to find area, we use pi r squared. R is that, so 0.0125 squared. That's the area. And mu naught is 4 pi times 10 to negative 7 Tesla meter per amperes. And then we got mu naught, and then N1, number of turns in the primary coil or the solenoid, is 600. That over L is the length, which is 0.25 meters. And then we have this thing, delta I over delta T, which is delta I is 0.5 amperes. Let's see if I can erase that. Okay, so delta I is 5 amperes and delta T is 0.60 second. Okay, so we need to do that calculation, and that calculation will give us the EMF. Okay, I will let you guys do that calculation. That should give you EMF in volts.